This series of tutorials will be making a live looper sampler. You should see an example of this, of the finished product, more or less, working there. I haven't made a video of it. And this is one of those tutorials that I'm just going to take you, from soup to nuts through the entire project, just coding more or less in real time. I mean, I've done it, so I'm just going to sort of remake it. And we might make some changes along the way. And I'll try to keep these segments to 20 minutes or so, but there'll probably be lots of them because this is kind of a big project. But hopefully take you through the whole thing. I mean, we'll be using Super Collider to synthesize the sounds, and processing for the graphics area, processing/Java. All right, so let's get started with just some architectural ideas. We're going to get started in the sound making place. So the idea really is that we're reading a buffer, okay? We're going to record, well, first we have to record into the buffer. So this is live looping sampling. The I've been doing this for as long as loopers have been around. Real famous one is the cost looper, Loopstation. Artists like Reggie Watts, for example, have become quite popular now doing this sort of looping thing. So hopefully this will provide some of that functionality. And it's also just a great way of learning some, going through a project and learning quite a bit about, about live sampling and about how to sort of create an interface that's useful. And then, I mean, obviously you can have this code and then modify it. And that might be the easiest way to get started. Some modifications. Okay, so let's get started with just this idea of buffer. So I'll try to explain things in fairly detail. Obviously, if it's too slow for you, you can move ahead. If it's too fast, you can pause and repeat things. So what we're going to do is, we're going to record into a buffer and we're going to read out of that buffer. So let's just simply look at, let's look at buff. It doesn't matter. We can do buff, buff record. Buff read RD. Let me just see buff write, right? The other one's called buff write. Okay, and let's just have a look at that. So buff write is a UGen that will write a buffer. So I guess the idea of a buffer, if I would even take a step back from that, is that just like we play a file out of our hard drive, we have an MP3 or a AIFF file on our hard drive and music, and we just play it using iTunes or something like that. It's just reading directly from the hard drive. In Super Collider, or in this sort of application, I want to be able to, in real time write some music or record some music and then play that back. So we use buffers, which are stored in memory, in RAM, and have a little bit faster access. So we just have to learn to set that up, which I'll get to, soon enough. So we're going to have to set up a buffer, and we're going to have to write into that buffer, et cetera, et cetera. Okay. So basically the idea is with buffer read, and there's a number of different ones. There's buff play, I think, and buff record, and those are maybe more standard ones if you're doing sort of recording or writing to buffers. But I'll explain to you in this tutorial why we're using these objects, buff write and buff read, mostly is because they are being read a modulatable phase index into the buffer. In other words, these objects, buff WR and buff RD, require that you have another UGen that's like the counter. That's like the the little dial that moves through. It's like the playback. If you want to go all the way back to say either turntables or audio tapes. It's the motor that moves the record around. So you need a motor in here that's going to move through the buffer. If you don't put anything in there, it won't read anything, even though it's, trying to look into the buffer. So that gives us, the reason we do that seems like a lot of work, but the reason we do that is that gives us a lot of control as to where we read it, how fast, how. Once you can put a UGen in here, then you can do a lot of different things. So UGen meaning something like you can use line, but the most common one is to use this thing called phaser. Okay, phaser.ar. Phaser basically just is an audio rate generator that reads from 0 to 1 in a certain amount of time. And that's what you need here. You just need something that reads from 0 to 1, and then we'll do some multiplications and such like that. Okay, so that's the sort of reason, and that was quite a bit of theory there in the first bit. But you'll see it gets a little bit easier, and we'll be dealing with these concepts over and over again, so that by the end of this, it'll be pretty second nature, hopefully. So, so the one kind of, I don't want to call it an innovation, but the one sort of perspective that I'm taking with this, or the one approach I'm taking to this, is to make that phase, this index, an independent thing, an independent object, or in this case, a SynthDef, so that we can have an indexer that we can read through many different buffers, for example, or we can make several indexes that are independent, that can be sped up and slowed down, or read from certain cue points. So if we want to loop just a section, we want to record, say, a minute of music, but only loop, say, the first 10 seconds. We can modulate. You can create a SynthDef that allow you to do that directly. But this is kind of it adds a lot more flexibility, and it also allows you to network these things. I mean, there's a lot of possibilities. I think it's a good way to do things. So that's what we're going to try to do. Okay, so now that's what we're going to try to do. We're going to create just an independent indexer that's going to help us read through these files. Okay, so yeah, so I have the cheat sheet there. But maybe let's see. Maybe it's worth just running some of these examples just to see what I'm talking about. Okay, so I'm just going to copy all these examples over here. Okay, so in this case, in the first case, we are creating, so we're just booting our server. That's all that does. Okay, or saying the server is a localhost server. I guess I need to boot it. Okay, and then so I booted the server. Now this one, it's using messaging, OSC messaging. I mean, it's server messaging, which I won't get into right now. I'll show you a different version, but this is just allocating a buffer, okay, on the server. So it's at the sample rate on buffer number 0, and so the 2 seconds. So it's a sample rate times 2. So buffers count in numbers of samples. So that's how many slots you have to reserve. So if you want a 2-second buffer, you have to do the sample rate 44.1, which is a typical sample rate for most digital audio these days. If you happen to be doing like 96K, you'd put 96,000 here, and then multiply by 2, so that means you get 2 seconds of audio. So you're going to basically, it's kind of like an array. You have this giant set with whatever it is, 88,200 slots in it, and you can fill that each with a sample. All right, and then in this case, we're writing into the buffer with buffer write. So we're using the UGen buffer write. And I'll go through all these buffer rate scales and stuff like that later, but we're just writing this sine wave oscillator with this noise is just helping you pick a random frequency between 300 and 400. All right. And it's writing into the buffer. And this is the phaser object. That's the one we're going to be using today. That just goes from 0 to 1, at a certain rate. Okay, so here is everything incorporated into one sort of object. So let's go. Did we send this already? No, we didn't send that. And then we're going to write that into it. And then this just reads it out. So you see that buffer write and this buffer read. It's the same kind of thing. It's a phaser. Okay, so read it back out. And then you can set the rate of the buffer different, etc. Okay, so that's the benefit of using this buffer read write and the phaser object. Okay. Now instead of incorporating my phaser now into the SynthDef, well, this is just a function, but essentially the same thing. I'm going to make that an independent thing, and I'm going to read that into a bus, an audio bus, and then I'm going to let my buffer read and buffer write things read from that, so we can have a synchronization. So that's the main benefit of having an independent phaser, an independent object. You can sync. And this will also sync our graphics too. So it's really handy to use. So let me get rid of all that. And let's just start here with our SynthDef that's going to be our indexer. Okay, so I'll try to keep my nomenclature the same. I call it buff index. Okay, so SynthDef, let's set up our SynthDef. And we're going to call it buff index. Buff IDX. And then I'll set up my function. That's going to be do all the heavy lifting. Finish my SynthDef and do .add. So that's adding this business there. Okay. So the main object we're going to do, so let me create, we'll add arguments later, but let me create a variable called, again, I'll try to keep my nomenclature the same, indexer. Okay. Okay. And just to give you a heads up, a lot of this stuff now, it's going to be a little bit plotty, but a lot of it is just really reconverting whatchamacallit, units, really. Okay. So sometimes we're dealing with samples, sometimes we're dealing with seconds, sometimes we're dealing with just a normalized number, 0 to 1. And it's just a lot of what we're going to do here. It's not super complicated, but a lot of what we're going to do here just has to do with making sure we know where we are. If we're dealing with samples or doing with a normalization, or making everything sure everything's equivalent. Okay, so our indexer is going to be this phasor. Okay, equals phasor.ar. Okay, and like I said, a phasor is an audio rate object, so it's running at 44,000, whatever the sample rate is, 44,100 times a second. So a nice quick audio rate. And it has a number of these things. So trigger will, once we send it the trigger, it will reset back to whatever value we put in there. So if we put, if we send it make trigger an argument and send it 0, it'll go back to the beginning. Okay. So let's see, I don't think I even used the trigger. Oh no, I did do trigger. Okay, so T, I don't know why I typed the thing in, but I guess just to be explicit. So our trigger is just going to be 0. That means it's just automatically going to start at 0. Rate. Okay, so the rate is, we have to use this object called the buff rate scale. Okay, so let's go look at that. Okay, it returns a ratio by which the playback sound file is to be scaled. So that's always a bit confusing. It was always a bit confusing to me. All right, but basically, it's an object that allows you to get the rate of the buffer. So the sample, let's say you record a 2-second sample, it's going to calculate, a sample by sample rate at which to progress. So if I wanted to, for example, play a 2.3 second sample back at normal speed using this phasor, it's going to calculate. So if this phasor is running at, basically it's going to make a calculation that says that this phasor is running at 44,100 times a second, how many samples would I need to read every sample, every period, so that I play the sound file back at a normal rate. Okay, so basically, 2 seconds will be, it'll go from 0 to 88,100 or 200, right? Okay, but you can just forget about all that and just deal with it by using this buff rate scale object. It's a control rate object. Okay, buff rate scale .kr. All right, and then it's just gonna ask for your buffer number. So it's gonna figure out how to scale that particular buffer, and then it's gonna make sure that phasor runs, so at that right rate, so it can run as it progresses through. It's gonna read it through at the normal speed. Okay, so buff num. We're gonna call that buff. So we're gonna make an argument called buff. That's gonna be our first argument, and this buff we're not going to put a default there because we don't know. So when we instantiate this synth, when we make a synth based on the SynthDef, we have to give it a buffer name. So I'll show you that later. Basically, you're going to create a buffer for you to write into, and in this case, we're going to create a buffer just for the index. Okay, and we can create several indexes, so we can do things at different speeds and switch between them. All right, so we're going to have that buff rate scale times buff. And then the whole thing, so it's going to calculate the scale, but that it'll kick out a number, or really a signal, a control rate signal, but that represents a continual number. And then that's going to be times the speed, SPD. So we'll create another argument here called speed. Okay, and we're going to set that default 1. So speed is how many times speed. So if you want to go 2 times as fast, you use speed 2. You want to have as fast, speed 0.5. Okay, so what are the next arguments here? Oops. Okay, and a start and end. I believe we're going to have those as well. Start and an end. Okay, and then there's this reset position, but I don't believe I use that. I might at some point, but we'll see. All right, but we have to use the buff frames. Okay, so start and end is a let me just give it a little extra space so we can see it. Start and end, it's based on it because phaser is running from 0 to 1. So I'm just going to close parentheses and put a semicolon so I don't forget to do that later. So start and end basically is a 0 to 1 number. So 1 will be the very end and start will be 0. So you have to modulate that by the number of actual samples in the buffer, right? So if I want to start at halfway through the buffer, I would do it at, I guess, 0.5, but buff frames, right? But I would have to know the number of frame, right? So if it's, let's just look at that and just. So that, again, this is the part that gets a little confusing, but it's just a conversion of units, huh? So if we understand if we just understand that the basic point is that we need to convert these units. Okay, so the current number of allocated frames. Okay, so that just means how many frames are in the buffer. So if we have a 2-second buffer, it's going to be 88,200, right? So if you want to go halfway through, we're going to do 0.5. So our start will be say 0.5. We'll do 0.5 times 44.1, which will take us to 88.2, which will take us to 44.1. Then I'll be halfway through the whole buffer. Okay, at sample number 441001 maybe, I don't know. Anyways, one of those. Okay, so, and then of course you can adjust that for seconds as well. You can do so many seconds as well, but we're going to do this as a normalized number, a 0 to 1. So start will be 0 and 1 will always be the end. I mean, the real end will be 1, and we can go anywhere at anywhere into it by using a number between 0 and 1. So start times, we're going to do buff frames. I think that's a KR as well, and then buff. So this is going to all these things are specific to a buffer. Okay, so they refer to the actual buffer we're using. So it does some calculations, automatic calculations based on that buffer, and then buff frames .kr and then buff. Okay, so let's finish those arguments. Start is going to equal 0 as a default, right? We're going to start at the beginning, end at the end, equals 1. And I'll save that. Let's make sure that's what, yep, and 1. Okay, so there we go. So this is really going to run, it's going to run. So a thing we can do here is to poll this, and you can see what actually happens, all right? So if we do at the end of the phaser, so this is the closing of my phaser object. You can tell because that turns red as well. So if I close the phaser object, and then if I do at the very end of the phaser object .poll, that'll give a real-time readout. And then a equals synth, and I instantiate the synth or create an instance of the synth. And then based on buff index. Okay, and hopefully this works. My server's already booted, yeah. Okay, well actually, let me just restart it all. Boot. So I was doing some other things there as well. Send that, oh, okay, so it doesn't like I did something wrong. It says buff rate scale .kr. All right, because I use this trig, it's looking for me to label everything. So I'll just get rid of that. I think I should be okay. I think I pretty much did things in order. Just recall that you can put arguments in their order, or if you don't want to do something out of order, you actually have to label it. So you have to, if I want this to be rate, I do that. Okay. Or if I want it to be reset position, I do that. Yeah, see it turns bold there. That'll allow me to skip those. But if I put it just like that, it'll just be whatever is in that slot rate. All right. But I forgot also that if you start labeling, then you have to label everything else. Otherwise, it won't automatically. It annuls the you were doing things in order convention. So then you have to do that for each one. But since we have put everything in order, let's just save a little space. And just so you realize that the trig is just a hard-coded 0. So it'll always goes back to 0 when you trigger it. All right, so let's see if it'll add there. It does. And if I do that, I should get the poll. It's 0 because it doesn't have a buffer. right? Okay, so that is a problem. So just so we can demo things, we're going to, and don't worry about these arrays of buffers just yet. We're going to do like they say, we'll create a buffer here. What do I use? Do I use the alloc? Yeah. Okay, buffer dot allocate. So let's look at that. So I'm going to say b equals, I'm going to create a buffer to store my index, basically. All right. So if we, I wonder if we can look up this whole thing. It doesn't look like it, so we'll just do buffer. Buffer. Sorry. Let's just look that way. Okay, buffer. And then, so when you buffer dot allocate, it's looking for the server, the number of frames that you want to allocate, number of samples, and then how many channels. And then there's other things you can do as well, but we won't worry about that. So let's go ahead and give the server, it's just going to be S. It's going to be the server we always use. Number of frames now will be, depends on how many seconds you want. So how do I say? I say s.sample_rate. Okay, so in case you do change your sample rate, I'm going to do s.sample_rate. Okay, and that'll calculate the sample rate. So if I run that even now, it'll tell me my sample rate, which is 44,100. Okay, and then I guess I am, I've decided that this is going to be a 16-second or 16 beat. I'm just going to make a 16 beat looper at 60 beats per minute. Or what is that, 4 bars. So this is going to be a 4-bar loop, you know. So we can adjust that. That'll actually be one great area to adjust later on. So I'm going to do sample rate times 16. But, you know, we can make that a variable. Let's do that now. Okay, so we're going to create a variable, and I'll use this global variable convention, and that'll be num beats. Okay. All right. Well, we're going to have to do a whole calculation, won't we? Because we're going to have to do BPM and all that. Okay, so let's do BPM, and that's equal to 60.0, okay? And we're going to have to do a total beats, right? So this is for, you know, it's going to be this looping, continuously looping thing. So we want to find out how many total beats in our sequencer. I guess it's kind of a sequencer. So BTS, total beats, and in this case we'll do 16. I guess you can have half beats too, but that's fine. We'll just use the decimal, doesn't matter. And then we're going to have the number of beats per, oh, that is total beats. And so the thing, what this really represents here, times our sample rate, hope I'm not losing everybody here, we're doing a lot of sort of calculations, is the total number of time. That's the total amount of time, because this is looking for seconds. Sample rate is how many samples in 1 second, 44,100 samples in 1 second. And this is times the total number of seconds of our index, because it's going to go through, you know, it's going to want to index all the way through, run through our entire sequence, you know. So if I want to do at 60 beats per minute, 16 beats, that's going to equal 16 seconds, right? That's an easy one. But let's calculate that in case we want to change our beats per minute. So in fact, even though it just turns out to be 16 anyways, it really is, this is total time. We'll do that. Okay, our total seconds. T-secs. Okay, T-secs. And then we'll do it's going to be the beats per minute, right? Okay, and that's going to be divided by 60. That's the number of seconds in 1 minute, all right? So if we divide it by 60, we're going to get the number of seconds per beat, right? So this calculation represents the number of seconds in 1 beat. And if we times the duration of 1 beat in seconds by the total beats, that's going to give us the total time in seconds, right? So if we just run these here, it's going to report 16, right? So then we can put T-secs in here, the total seconds, into our buffer object. And I'll close that up so we don't forget. All right, so there's quite a bit of setup here and a little bit to go through, but bear with me. Right, so let's show you what happens if we put it at faster. Let's do an 80 beats per minute. And if I highlight all these and evaluate that, it's going to be 21 seconds. Oh, I went the wrong way, didn't I? Mistake here. So it's actually, sorry. Haven't had my coffee this morning, maybe. It's actually 60 seconds divided by the beats per minute. And that should give me the proper answer. So yeah, let's evaluate that, see what happens. There. So if I do 16 beats at 80 beats per minute, I'm going to have 12 seconds worth of buffer, or 12 seconds. One complete read through of my sequencer will be 12 seconds long. So this, again, this is all this complicated. It's not that complicated, but it's complicated. It's a bit plotty math to figure out how to convert one unit to another, how many seconds, depending on what our objects are asking for. So if we want to allocate a buffer, we have to figure out the number of samples. And in order to figure out the number of samples, we need the total number of seconds. So we can do, s.sample rate, which is the amount of samples in 1 second. And then we can times it by the total number of seconds in our complete sequencer frame. I suppose if you wanted to calculate beats, you could, but it would be the same process. You just convert it. And we want it accessible in terms of beats per minute, because that's what we're kind of used to. If you wanted to do it at a different scale, if you wanted to use milliseconds or seconds, you can do that as well. That would be probably easier. But we're going to create a sort of beat-based sequencer, I guess. So these calculations just necessary to get the total amount later. And we're going to change some of these names later. I'm just going to keep that there for demonstration purposes. All right, so what we need is a buffer B that's going to be at that 16 seconds, so 529 200, which I presume is, let's change that to 60, sorry. Let's change that back to 60. And 705 600, I presume, is 16 seconds worth of audio rate, and it's a buffer, okay? And then we'll create this. We'll just send this again. I'm sure it's still in there. And then we'll create this buffer index, except we'll have it now at the buffer argument will be filled into B as the buffer, okay? So it says buffer number in the phasor thing, or in the buffer rate scale, it says buffer number, but if you just refer to the buffer, it'll automatically put the buffer number in. Okay, so hopefully this works this time, and it does. See, it counts through all the way through to whatever that number was, 8 something over 16 seconds. Okay, so it's pulling this phasor, and then back to 0. So that was 16 seconds there. Great. Let's stop that there. Okay, so that's just a demonstration of what this does. Basically, this is just a counter, really. It's like I told you, it's like the motor that moves a turntable, or I don't know how many of you might remember the old counters on the tape decks. You'd have these tape decks, and they would have a counter to tell you 1, 2, 3, 4, 5, 6. You would just roll, and that's basically what this does. So it drives the whole thing. So now you can use this in various objects. Okay. So there's a couple things we need to do. We need to make it accessible, and then we need to be able to change a few things. All right, so the first thing I'm going to do, which seems like I'm doing a lot of converting back and converting here, converting back, and there's probably an easier way to do it. I'll admit to that right away, but this is the way I chose to do. So I'm going to index this according to the buffer, the number of frames in the actual buffer here, depending on how many seconds. But then I'm going to change it back to a number between 0 and 1, because that's an easier number to work with, so that I can read through, basically meaning that I can read through various other buffers at the same rate, okay? And it'll be easier to think about it in terms of 0 to 1. So I'm going to go INDEXER norm. I think that's what I called it. And then I'm just going to normalize it, okay? I'm going to use one of these conversions. I've done this a couple times before. It's nice and super collider because it's all built in. Okay, and it's just basically taking this indexer number, which is running from, depending on the buffer, 0 in this case to, whatever it was, 8,000 or something like that, 7 what is that? 701,190. Okay. This is going to just index that to make that a number between 0 and 1. So it's going to do INDEXER, which is that long number between 0 and 701,190, or whatever you choose it to be, depending on what beats per minute you put in. All right. And then what total beats you put in. And it's going to go .lin. So it's going to do a mapping, a conversion, linear to linear. All right. And it's looking for what I want to, what I want to convert is the indexer. It's that number. It's looking for the min in and max in. So it's going to go from 0, 0, and it's going to go to what? The end. How did I put it? Buff frames and then the buff, right? So the total number of frames. It's going to go to buff frames. And, oh, right. Sorry, I'm realizing that I have to do another calculation here. So yeah, there were some things about that weren't working, and I realized that actually, if I do change the start and end times, I'm going to have to recalculate the total number it goes, the indexer. Oh no, it's still calculating that because this. Never mind. Okay, the indexer will go between those two numbers. Then instead, it'll still be the total buff frames .kr. So that's going to give me the total number of frames in the buffer. That built-in calculation. Of course, you can do it. Presuming your sample rate doesn't change, it'd be similar if you just did, 44 100 times the total seconds in the buffer, 16, whatever. Okay. But this makes it very fluid, so that if you change the buffer, change the BPM, et cetera, you're going to get the right calculation always in here. So it's going to start at 0. It's going to go to the total number of frames of that buffer, and it's going to convert it to a number between 0 and 1. And that's all you want to do. So let's pull that and rerun that and see what it gives us. It should give us a number between 0 and 1 in 16 seconds. So you see it's climbing very slowly. And at the end of 16 seconds, it will give us 1. And then restart. Okay, yeah, so that's the one thing that buffer does, is just restarts. Just continuously gives us this. So there's a great little indexing head, a great little object to do indexing. Okay, now we have to establish where we're going to go out. Okay, so I'm going to take it out 2 buses. I'm going to take it out to an audio bus, and I'm going to take it to a control rate bus. Okay, the audio bus will be for any of our internal SuperCollider audio objects. So if we want to run a buffer read or buffer write, those take in audio rate indexers, audio rate phase, phase information, basically, where you are currently at in the buffer that to be read. But also I want to send out control rate information, because that'll be useful in controlling our graphics. The audio rate is too much information, too quick to be handled, especially if we're sending it remotely over OSC. And it's overkill, to be precise, also because our eyes, our visuals do not work at audio rate. In fact, the standard, what is it, NTSC or whatever standard for most video we watch is what, 29.9 or something like that frames per second. So compare 29.9 or anything even close to that, even if it's doing 60 frames a second or 120 frames a second, to 44,100 frames a second, it's just overkill, So we're going to have a control rate as well. Okay, but we have to create these. And again, this business, I'm going to go through in a future tutorial. I make a bunch of them so we can have an array of them, so we can have several different buses and several different buffers for each of our audio tracks. But right now, we're just going to create let's do let's make these for now some kind of global variable. So IXB, make an index buffer, and this will be these will be buses. This will be IX we'll make a bus, and then we'll make an IX index audio bus and an index IX control bus, K bus. Okay, and then this will be equal to, we're going to create a bus. So the idea of the buses is that I know I've covered this 100 times, but for those of you who don't know about buses is just like it sounds in, say, audio buses. Like if you're thinking about a mixer, SuperCollider allows you to create these buses. So if I'm sending something out, bus number audio bus. Oh, so yeah, so you can create audio rate and control rate buses. Let's just talk about audio buses, just like a patch bay. If I want to send my audio out to channel 0, it's probably going to come out my left speaker. Out to channel 1, it's going to come out of my right speaker, et cetera, et cetera. So I can patch it to any of my outputs. But I also can patch it to what we call private bus. So I can just put it onto like a mixer channel that doesn't go anywhere, and then use that, then route that eventually somewhere, and route that dynamically like the patch bay. So I can plug it, say it's going out to private bus number 29. Then I can patch 29, like in an audio network. You would have, say, maybe mic 3 coming in to your patch number 29, and you can patch number 29 to one of your speakers, to the house or to the lobby or something like that. Okay, so in this case, we're creating private buses to send this information out, and then when they're needed, the ones the SynthDef will develop in the future, we can grab them from these buses. The data will just be going to this bus, going to this bus, going to this bus, and when we actually decide to use it, we'll patch it using kind of a virtual patch bay, patch it into the place we need to use it. All right, so let's create a private audio bus. So that's easy enough. You go bus.audio, and then you have to designate the server it's going to be on. It's going to be S, and the number of channels is just going to be 1 channel, like that. All right, and the control buses are very similar, except you just make a control bus control instead of audio dot control. Okay, and then this is looking for server and how many channels 1. Okay, so you can make multi-channel buses as well, but we won't get into that right now because we're just dealing with mono single channel buses. Okay, so now these have been created. We're going to send this information. So right now this information is being calculated in our SynthDef, but it's not able to be used. It's not going anywhere. And remember the great out UGen. It's just a way to send it out to our hardware, essentially. But you can also send it out to private buses, okay? Just like you can send it out to one of your audio channels, which are connected to your sound card. You can also send it out to a private audio channel. So I'm going to do out.ar. And we're going to send it out to bus. Now we have to create some arguments because we have to designate what those buses are. So we'll have a bus. And we won't, just like the buffer, we won't know which ones until we actually make an instance of it. So we'll do that. So we'll just leave the default blank. And then K bus. All right. So this is going to go out to our audio bus. This is the audio. It's going to send this indexer information, this normalized indexer information out to audio bus. Okay, AS. And then the channels array is going to be the indexer norm. Because even then, audio, I'm pretty sure we want the. Oh no. So audio, we're sending out the indexer, so we don't have to recalculate it. Oh, right, but the indexer norm is to send out because we want 0 to 1 information to manipulate graphics, okay? So we're going to send the pure sort of indexed phaser that's counting the number of frames, because our future objects like buff read and buff write just want what frame you're on, okay? And then we're going to send this out to the normalized one. So this is K bus, okay, and this is going to be the INDEXER norm, NORM. All right, so it's sending 2 outs, one to a control bus and one to an audio bus. All right, and then I think I put a few little notes there in the final code, which you can get from GitHub. Right. Okay. Okay. All right. So we're just probably getting there. I think my thing's going on long. So, oh yeah, this is like a double feature tutorial. I'm not sure I'm going to be able to make 20-minute videos because it doesn't seem like I get enough done, but we'll see. Maybe there'll be 40-minute videos then. All right. So we're almost to a good stopping point, but let's get to a good stopping point. So that works, and you can see. Well, we already saw that it's coming out these 2 things, and it's sending to these buses, and it's just sitting there for us to use, and we'll create things to use it in the future. The only other thing that we have to set up architecturally, so this is, let me just take a few minutes here to describe some of the area which can be sometimes confusing. So I want to try to describe it a little more carefully in SuperCollider. So SuperCollider is metaphorically creating audio. It's actually kind of creating audio, digital audio, but there's that metaphor of audio that sits on top of SuperCollider. So the sort of what I was talking about, where you send your audio signals. So in the physical world, we would use these cables and patch our audio signal. We'd take a microphone and plug it into, say, if we're working in the theater, plug it into like a floor box, and then that audio signal would physically go up to a mixer or up to a patch bay, right? And then we'd patch that bay into our mixer or an effects station or something like that. And then we would patch our mixer back into the patch bay maybe, and then patch our mixer over to our patch, then use that mixer patch bay to patch out to the house, the speakers in the lobby, on the stage, wherever, monitors, etc., etc. Okay? So there is that metaphor that sits in SuperCollider. So we are actually patching audio signals back and forth, and we're using this very similar idea that we're like a mixer idea. We're sending things to patch bays into mixers and such like that. There's also a flow of data too. So obviously SuperCollider is a programming environment as well. So we have to sort of learn to separate those two, or learn to think in those two different worlds. So there's a certain order of operations in the programming things. We're sending sort of digital signals around. Various variables are being sent through things. Information is being run in certain order and such like that. And SuperCollider also has a kind of a patching, what they call the node system, as to when things are executed and what things are executed before other things. Okay, and that has an effect obviously on our audio, because we're using digital, we're using programmatic means, we're using computer control to manipulate these signals and then eventually create audio for us. All right. So all that to say is that we also have to manage the way our data flows within the programming environment, but we try not to be confused with the way the audio is flowing in that metaphoric audio environment. Okay. So we need to create these things called groups. Now, groups are helpful in that collect processes under one header, and then you could use groups to say this group of processes get executed first, and then this group of processes get executed second. Okay, so in our case, we want our indexing processes to be run really before everything else, so that that index is sitting there already being calculated for that frame, for that one, whatever one. Well, I guess in this case you'd call it a frame. So everything that's being a program is running, and then it reruns itself, reruns this loop. So we want to make sure everything in this one loop gets calculated, and then the next thing that wants to happen. So that's pretty abstract. Let me show you what I mean. So the index needs to be calculated first before we can use the index to read, say, a buffer and stuff, and you'll see what happens when we go along. So we're gonna try to keep the so we're gonna use groups, and that's one way. There's a number of ways to handle this, probably better ways than I've done, but this is what I know for now. So we're gonna call a index group. Okay. I'm going to create a group. Okay. I think, do I have to do .new? Yes, .new. You might not have to, but let's do .new. And then it's expecting the target, which is going to be our server S. And that's it. So we're going to create a group called index group. And we're going to send this and so the groups talk about nodes or synths. We're going to send the actual synth, not the SynthDef, because remember the SynthDef just sits on the server, it's ready to be used. But we're going to send, when we actually create synths, we're going to send the synth to sit in this group. So we make sure that these get executed, all the index things get executed before the other things, so that the index information, it's run through all this stuff here, and it's available to be used by future things like reading and recording and stuff like that. So you'll notice later on, I create in groups for all my incoming audio, so all the record, and then an out group for all the outgoing, so that in terms of programming, in terms of data, the indexes get run first, so they're running and they can be used by the records. So we use the records, and then they can be run by the plays in case you're recording and then playing back at the same time, simultaneously. Then your record audio will come out it's being written to the buffer first before it's being read from the buffer. Okay, so that'll just determine the order of operations these groups do. Okay, but it's separate from the audio. So you might have an audio that does order of operations a certain way, but you might, sort of data, but then your audio might follow a different route. But they're two different worlds. Okay, just try to keep that in mind sometimes in sorting this stuff out in your head. All right, now to add the synth to the particular group, we have another set of arguments. So you notice here, it's just like a UGen or anything else. Synth is a method or a object in SuperCollider. It's looking first for the def name that we're using, the SynthDef name, which is buff index. Then it says the arguments, which, as I mentioned before, has to be enclosed in an array in square brackets. So we can put in as many arguments, initial argument settings as we want, as there are. I can put any of those in. Okay. So in this case, we do actually have to add some arguments. We're going to add the A bus. Is going to be this one. IX. Oops, let me make this a little better. It's going to be this IX A bus, right? That's our audio bus that's going to send out audio data out to. And then our K bus, this guy here, this argument here, it's going to be the IK bus. Okay, it's going to send out to this control bus, right? Okay, and then you notice after args, another argument for the synth is the target. So our target is going to be this group, all right, the IX group. So tilde IXGR. So that means it's going to target that group, is going to send this process to that data group. So that process will be run in the order of the groups. So if this group is the first group, it'll run all the things belonging to that group first, and then they'll run the next group next, and the next group next. So that's where we kind of can assure an order of operations. All right, so that's been an extra size, big size tutorial. And we're just starting to create our looper sampler, starting to try to create the audio bit of this. And this is maybe the most complex one. It's a pity that it's our starting one. Maybe I should have started somewhere else. Okay, but basically what we've done today is we've done a lot of preliminary work, a lot of setup work, and we've created this buffering index. So this indexer, that's really just a counter that will allow us to pop into any of the recordings or writings and keep everything synced together. So if we're syncing, recording, and then the next pass around or it's playing back from that same area. And if we have multiple tracks and such, it'll just keep the index synced for everything. So it's nice to have a separate indexer. So we created a SynthDef that's going to use this phasor object, and it's going to write the results of that phasor object, a normalized version and a frame rate version or sample rate version, out to two places, two private sort of holding tanks, an audio bus and a control bus. Okay. And then in the next tutorial, we'll learn to write to those buses based on this index, or write to a different bus, but based on this index. We'll use these buses to grab our index information, and then we'll write to another, an actual audio bus. Okay, and then we learned about the fact that in the data flow or the order of operations in our programming environment, we also need to sort of designate what comes first, what comes second. And SuperCollider provides you a way of managing this called groups, so you can manage the order in which things are executed as data, not as audio necessarily. But though a lot of times they're the same thing, or they follow the same sort of order of operations. Okay, so when we create or instantiate or create a synth that's going to run our buffer index, it's going to start these processes, these phasors, and this normalization, and send these out. And it's going to start it in this group. All right, and then we had to designate the buffer number, which we allocated here as based on the beats per minute and then total number of beats in our sampler or sequencer, sampler, looper, whatever you want to call it. And then we have an audio bus and a control bus that it gets sent out, and then it's sent to that group. Okay, so hopefully you made it through that one. Bear with me, and there's more to come, stuff that actually does stuff that'll be a little bit more, maybe more accessible. Okay, well, good luck with that, and I hope this helps.